Hello everyone, today we'll talk about the problem longest continuous subarray with absolute diff less than or equal to limit. The name is very long and self-explanatory. We're given an integer array and also some limit. We're interested in finding the longest contiguous subarray such that the difference between any two elements, when it comes to its absolute value, is less than or equal to the integer limit that we're also given. So, how do we do this? Well, observation 0 is that this is of course the maximum of our array minus the minimum. So for a subarray of the original array, we just take the maximum and minimum, because the absolute value of the difference between any two elements is always less than or equal to the difference between those two special elements. The first real observation in this problem is this. Assume that we want to know if this subarray is good. And we know that this subarray is bad. Bad means that the difference between the maximum and minimum element in that shorter subarray is greater than limit. Well, obviously, this whole bigger subarray is also bad. We cannot add more elements and expect the difference between maximum and minimum to suddenly become smaller. So we have this subarray monotonicity. And this is a very useful property when it comes to designing algorithms, because it allows us to do things in a smarter way than just looking at all the possible n squared, about n squared, subarrays. In particular, one common use of this observation is that we can consider, let's say, every right end or every left end. So in a whole array, we consider everything ending here, then ending here, then ending here, and so on. And we find the leftmost position, which connected with our end, is still a good array. And we know that if we now move the end forward, and forward and forward, then this end can also only move forward, from what we've seen previously, because we add more elements. So we can at most destroy our good property, and we have to fix it by removing elements from the left. And that means that those two pointers will traverse the whole array only once, which means that we only look at a linear number of possible subarrays. And this is called either a two-pointer technique or a sliding window technique. Some people think about sliding window as a window that doesn't change size. So looking at this, then looking at this, then looking at this. But whatever you want to call it, just know that this is a common and useful technique. And step 2. How do we know what the max and min is of our array? There are many ideas here. The most cheesy way would be to use an RMQ. Range minimum query or range maximum query, whatever you want to call it, because it's the same structure. For instance, you can use a segment tree, or there are other ways to solve it in time that is not too big, so either constant or logarithmic for every step. And, well, this is the most cheesy solution, so let's see a wheel of cheese. But this will just solve it. So we have our two-pointer technique, we look at the right end, we have our current left end, and we just look at the maximum and minimum in this array, and if the difference between them is too big, we have to push the left end forward. Again, we query our RMQ for this subarray, and so on. So that is one way. Now, this is a very brutal way, but it will still be fast enough. A better way would be to have a set. No, well, mostly multi-set, right? But for us to keep all the numbers that we have currently in our subarray in some data structure that can tell us what's the biggest number, what's the smallest number. It can add numbers because we add numbers moving here, and it can remove numbers because we remove numbers moving here. And everything can be done just by using a set. And a multiset here because our numbers can appear multiple times in our array. So this will also have a linear logarithmic time complexity. And it's not as dumb as just using RMQ because it uses the fact that our window doesn't change too much. And now, can we make it even faster? Can we remove that logarithmic factor? Well, if it was just sum, then of course we can, because if we look at the sum of subarray, then here we just add numbers, here we subtract numbers, and it's very easy. However, it's not that easy to add or subtract numbers when we are looking at minimum or maximum. Because it can be that we subtract a number, which is not a minimum or maximum, but later we subtract the minimum or maximum, right? We remove it, and suddenly some other number becomes minimum or maximum. And how do we know what number it is? Because if, let's say, we have here a number that we remove, then we remove this number, and this number was max. So now there is a different maximum. And if the different maximum is somewhere here, then we can take it. However, if that maximum was here, then we know that we cannot take it, because we have removed it. However, maybe this value appears again in the latter portion of the array, so we can take it. It seems pretty difficult. Or rather, we know that we can do this using a set, but this gives us a logarithmic factor. But without the logarithmic factor, we don't know how to do it. But there is a way, and that way is to remember all the numbers still, not in a set, but in something simpler, but not really remember all the numbers, only remember interesting numbers. And for instance, what numbers are not interesting? Well, if we have a number here, we have a number here, and we have a number here, something between them, and they are all in our current subarray, and we know that A is greater than B, and C is also greater than B, then B can never be a maximum in any subarray that we'll look at, because we'll push the right and forward. So for as long as B is in our subarray, C certainly also is in our subarray. So we don't have to remember B. In fact, we don't have to remember B as a maximum, even without this A here, so we can forget about this. And if there is a greater element to the right, then we don't have to remember that B exists. It will never become a maximum. So what elements do we have to actually keep in mind? Well, maybe the last element in our current subarray, it can potentially become maximum. We don't know what's after it. If everything after it in the original array is smaller than it, then finally it will become a maximum, maybe. And then any earlier element, for it to become a maximum, it has to be greater than that number. So in other words, we maintain a list that we can add and remove from some ends, so we have to specify that later, but it will be sorted, and those will be all the possible maxima. So it will start with the biggest number. This is the current maximum, and then we have the biggest number after this number. So because maybe we remove it at some point by pushing the left and forward, and then something else becomes a maximum, then this will be that maximum, then a smaller number, and so on, and finally this will be the last element in our current subarray, because it can always become maximum. And now whenever we add another element, then you just have to keep in mind that if it's greater than any previous element, then those previous elements cannot become a maximum, so we have to remove it from our list. So let's say we remove this one, this one, this one, and finally we, of course, since now we have a new rightmost element, we have to add it to our list. And then when we push elements from the left, if they are equal to the current maximum, then you have to remove them from the left. So we have to remove from the right when we add new elements, add another element to the right, and remove from the left. So we'll just use a double-ended queue, because it supports adding and removing elements from left and right. And of course, for minima, it can be the same thing. So this is not really a monotonic stack, this is a monotonic double-ended queue. But this is a way to, at the expense of linear space complexity, have those minima and maxima not in constant time, not really, but in amortized constant time, in the sense that every element can be added and removed from both those queues at most once. So that means that the total number of operations is at most linear. Since we go through all the elements, then it amortizes to constant time, so the whole algorithm remains linear. And again, let me remind you that you can also solve this problem simpler with either a segment tree or something like that that supports RNQ, or with a set. And let's look at the solution using what I've described here. So a subarray is bad if the biggest minus the smallest is greater than limit. So the leftmost element of both of those decks, highs and lows, we go pushing the right end forward. So this is the value of the right end. Left end is at 0. And here is what we've described when it comes to maintaining those decks. So you have to remove all those elements that are dominated by the new element and finally push the new element to the deck. And now while we have too big difference with our array, we remove elements from the left, and if these elements are leftmost elements in the corresponding deck, then we have to remove them. After that, we know that the subarray is okay, so we try if it's actually the largest subarray we've seen, and we return the result at the end.